Hi, welcome sa subject natin, Principles of Steel Design. And for today, we will be discussing a type of structural members, steel structures, and design philosophy. So our outline for today's lecture are as follows. We have type of structural members, we have different type of steel structures, and we will also try to explain what are the different design philosophies being used when it comes to the design of steel. For our learning outcome, at the end of this lecture, hopefully we will be able to differentiate the different cross-sectional steel shapes that we have in practice to explain the types of steel structures present in the real world, and to demonstrate to you or just explain to you the different design philosophies used in steel design. Okay, so to start, let's go back with our steel. So before last time, we already discussed the behavior of our steel when it is subjected to a tensile load, and we already discussed the stress strain diagram of the steel, wherein we identified some major points that we need to consider when we are studying this material. And based from this graph, we were able to identify the yield stress of our material and also the ultimate strength of our material. For now, we will discuss further some more properties or more details about our material. And here we have the grouping of structural steel. So it is said that structural steel is grouped into three types. So we have plain carbon steels, low alloy steels, and high alloy or specialty steels. So mainly yung groupings natin of these steels differ on the composition of the material or the elements within the material. Okay, so number one is plain carbon steel. So mostly iron and carbon yung composition niya with less than 1% carbon. So this type of steel, um, nilimit lang yung percentage, yung composition ng carbon. Kasi si carbon, it has a property na mag-develop ng strength but um, if medyo malaki yung percentage na carbon, nababawasan yung ductility ng member natin. Wherein yung ductility is yung capacity and property ng material natin to sustain very long deformation. And when it comes to steel, if ductility is compromised, it is not a very good material or it will not perform better, no? So that's why they limit it onto less than 1% lang yung carbon. Then we have low alloy steels. This is iron and carbon plus other components. So there are cases that we still need to increase the strength of the structural steel, but to account or to not um, damage yung ductility performance ng material natin, we tend to mix yung steel natin with other um, element that is of pwede dun sa material natin. So we have, ano ba, we can, I think manganese, we have copper. So these low alloy steels are that type of steels wherein other type of elements are present dun sa composition ng mismong material natin. And then we have high alloy or specialty steels wherein similar in composition siya ng low alloy steels but with higher percentage ng component added to iron and carbon. So we stated already na if we increase the percentage of carbon beyond 1%, the ductility of our material is being compromised. But to account for that decrease in ductility, it increase natin si iron. And iron helps the material to be more ductile. Kaya nakaka-counteract niya yung effect ng less ductility na pinuproduce ng more carbon. Pero pagdami ng percentage ng iron and carbon, anong nangyayari sa material natin? Our material tends to be more expensive kasi these elements are more expensive, and this type of steel are usually for special applications only. Kaya specialty steels yung tawag sa kanya. Okay? So some um, property that it may possess are resistance to corrosion, which is very important to steel kasi once corroded si steel, yung kanyang strength is nagde-deteriorate, no? So, we try to um, uh, we try to protect our material from those unwanted changes dun sa property niya. Okay? And then we go dun sa one type ng low alloy steel which is yung ASTM A36 or A36 for short. Okay? So yung A36 o yung 36 in general pertains dun sa yield stress niya. So we have here yield stress of 36,000 psi. So the 36 number here stated dito sa ASTM 36, that is actually 36 KSI wherein yung K is dubbed for kip and 1 kip is equals to 1,000 pounds. That's why 36,000 psi is also equivalent to 36 KSI. Okay? So, that's why 836 ang tawag sa kanya and it has a tensile strength or FU of 58,000 to 80,000 PSI. So, mapapansin natin naka-range yung value ng ultimate strength ni 836 because hindi once na manufacture si 836 hindi nakokontrol yung value ng tensile strength niya. But the code specifies na it should be at least 58 KSI. Okay? So, so it can be 60 KSI, 70, 75 until 80 KSI. Pero once na yung value ng tensile strength natin or FU natin is below 58 KSI, that means that our material is already not conforming to the prescribed by the code. So, sabihin substandard yung mismong material natin once na less than siya dun sa minimum na amount required by the code. Okay? And there are also two other materials na usually ito yung gagamitin natin all throughout this course. So we have yung ASTM A572 grade 50. So here, yung grade naman yung titingnan natin, grade 50. The 50 pertains also dun sa ating yield stress, which is also equals to 50 KSI. Then we have ASTM A992 high strength steel, which is the same almost ng A572 because they have the same property of yield stress and ultimate stress. So once you check yung nakalagay dito sa table, we have yung yield point, yung yield stress natin, Fy, the tensile strength, or yung Fu natin. We can see that for A36, as mentioned on the previous slide, we have 36 KSI. And for tensile strength, we have the range of 58 to 80 KSI. But for design purposes, we will just use 58 KSI to be more conservative. So kung halimbawa on actual practice, yung na-order natin na A36 steel would come out to be 62 KSI, okay lang kasi at least may allowance tayo for design. Pero dapat hindi siya bababa ng 58 KSI. So much conservative assumption would be to use 58 KSI as our ultimate stress. And we have now A572 grade 50. So for the yield stress, we have 50 KSI, ultimate strength of 65 KSI. The same with A992, 50 KSI and 65 KSI. So this three material again will be uh, the main materials, the type of steel material that we will be using all throughout this course. So I would suggest for you to remember the values of their um, yield stress and tensile stress. So remember these values, and these values. Okay, so that when we have a problem, let's say it's stated in the problem that the steel beam is using an A572 grade 50 steel, it is understandable that the yield stress that we will be using will be 50 KSI, and then the ultimate stress that we will be using is 65 KSI. So without even um, indicating the values of Fy and Fu, we should know it already automatically. All right. Then Now we go to the standard cross-sectional shape that we have um, commonly used in practice. So for hot rolled shapes, we have the following. So we have W shape and S shapes or American shapes. So as you can see here, these two material are almost the same. Ang distinct difference niya is the width of the flange. As you can see, the S-shaped material or the American standard S-shape is narrower than the W shape. And as you can see here, the flange of the S-shape is sloping inside. Okay. In general, we are using W-shaped sections because this is more prevalent here in the country. Okay, and more suggested or more um, usable because of the width of the flange. No, it's okay. So for the designation of our shape, for W shape and S shape, uh, we are using the two common designation. Okay, so the first letter is pertaining on what type of shape it is. And then the first number that you can see here is this is our W shape depth. Okay, but um, more the right term is nominal depth. Okay, so as you can see here, we have a W18 by 50. So as shown here, we have a height of at least 18 inches. So we dub it as nominal depth because not every shape will have an exact value of 18 inches. It can be 17.8, 18.2, 17.9, but generally can be rounded off to the nearest inch, which is 18 inches. Once you check the AISC construction manual, you will see that some of this shape, although it's stated that the depth will be, for example, 18, you will see that the actual depth will be less than or greater than that number. Okay. Then we have the second number, which pertains to the weight per linear um, length of our member. So this means since this particular designation is in English, this is in pounds per inch or pound per foot, depending on the table that you are looking at. But for metric or SI unit, for metric it would be kilogram per meter or kilogram per mm. Depending on the table that you are looking at. So you just have to look at the header of the table if what units is being used there para ma-identify nyo kung naka-English or uh, naka-metric yung ano natin. Okay? So basically, yun yung pag-designate for W shape and S shape sections. And then we have our angles. So for angle bars, the designation is somehow close with the first two designations, but for this case, the numbers represented are exact. Okay, so the first two numbers are for the width or length of the legs. Okay, meaning this portion. Okay, the width, and then the last number pertains to the thickness of the material. So when we say 6 by 6, it means it should be exactly 6 inches by 6 inches by 3/4. So yung last digit again is for our thickness. When we have an unequal leg, meaning our length or the width of each sides are not equal, the first digit or the first number should be the greater one, whichever is greater. Okay, so you will not see a designation as L4 by 6. It should be L6 by 4. And then again, the last digit pertains to the thickness of our material. Okay, And then we have the American Standard Channel or channel. So the designation is almost the same as W shape and S shape sections. So the first letter is for the type of shape, the first digit is for the nominal depth, and then the last digit is for the weight per linear length of your member. And lastly, we have the structural T. For structural T, the designation is the same as W shape and S shape section, wherein the first symbol is for the still designation, the first digit is for the structural depth, and then the second number or the last number in the name of the member pertains to the weight per linear length of our member. So for structural T, um, this is actually just the half or the cut version of the AW shape or S shape section. So as you can observe here, when you cut a wide flange in half, you can see here our T section or our structural T. So meaning if you cut this section in half, exactly in half, you will have the property for a structural T. So when we say WT 18 by 105, you are also suggesting that originally or in the code, there is a a W-shaped section that exists that has a dimension of W W18 W36 by 210. Okay, so you just double or get the other half of the property and then just check on the construction manual what is the values of its dimension. Okay, so these shapes are considered as hot rolled shapes. Okay, so later we will discuss what does it mean when we say hot rolled yung shape natin. Okay, so some other shape that we have that are not stated or available dun sa table dun sa construction manual are ito yung bars and plate natin. And when we talks about bars and plate, we can say daw na bar yung isang steel material if its width is less than or equal to 8 inches. So 8 inches is roughly 200 mm. So if it's less than or equal to 200 mm, we can call it as a bar. But when our width is beyond 200 mm, it would be called as a plate. Okay? So for uh, to make our calculations general, we will use the conversion of 1 inch is equals to 25 mm to change our unit from an English system to ASI system. So this is this is not the exact conversion, but we can use that value to arrive with a more um, constant or whole number values that we can use. Okay. Then we have this built-up shapes. So built-up shapes is from, let's say, you want to create a a section that is not available on the construction manual. Let's say for the W shape section, yeah, you intend to have a depth of maybe 1 meter or 2 meters depth, but the construction manual does not have a depth or a size for that depth. So you will opt to construct it by yourself by adjoining three pieces of plate, then welding it together to form a single member. So this type of members are called built-up sections or plate girders. Okay, so saan natin usually nakikita to? So usually application ito are sa mga steel beams na ginagamit for bridges. Okay, especially if it will be used as the main string element of the or the steel beam supporting the slab or nung carriageway natin for bridges. That will be a very shallow member, no? So ibig sabihin malalim na member. So Um, Kaya yung height niya or yung depth niya usually is greater than 1 meter. So you have to create a built-up section already. Okay. For this case, so you can see you have a cover plate. So main reason for cover plates usually is to increase the thickness of our flange. Maybe if yung common construction na available sa construction manual yung gagamitin, maybe sa design hindi pumapasa yung flange natin. So to help the section pass the required loadings, maybe increasing the thickness of the flange will help. Okay, so that's why nagwe-weld sa taas nung mismong steel plate. Then we have ito yung mga double angle and double channel na usually ginagamit for um, trusses. Okay, so usually our section we just installing it back to back with each other na may spacing lang, ano. So usually sa trusses to nakikita. Then we have dito, we have steel plate, steel pipe rather, and hollow structural sections. So for steel pipe, usually, it can be, may mga type pa din yung steel pipe. It can be standard, extra strong, or double extra strong na steel pipe. And then yung usual na designation sa kanya is yung kanyang outside diameter. So let's say this is a 10 inches. Okay? Yung diameter niya. And let's say we are using a double extra strong or extra strong steel pipe. So the designation would be a diameter 10 inches XXS steel pipe or double extra strong or extra strong steel pipe. So mainly nagiging siyang double extra strong depending on the thickness. So from the standard thickness, then once na ano na siya sa range ng standard thickness, then magiging siyang extra strong, and then after extra strong, extra strong. Okay? Then lastly, we have the hollow structural sections. So let's say we have a length of, let's say, 8 inches and then a depth of 4 inches. So to designate or a thickness of 3/4. So to designate this section, we will be designating it as HSS 8 by 4 by 3/4. So the same designation technique used in angle bars. So okay, yeah. So there you have it. Some of the standard cross-sectional shape. Okay. Then we go to the two type of manufacturing process that we can observe when we are dealing with structural steel. So as mentioned earlier, those sections available in the construction manual are hot roll sections. When we say hot roll sections, these sections run through a series of rollers while maintaining a very hot temperature para mas madali siyang mabend, ano, bendable siya. Pero habang dinadaan siya dun sa roller and then na kakas natin siya do sa desired shape natin, hindi nawawala yung ductility niya, which again is a very important property ng steel natin. So, since mainit nga siya or dumaan siya sa very high temperature, yung material natin is very flexible. Pero hindi nawawala yung ductility niya kasi after mong ma-cast siya dun sa desired shape mo, it will be cooled down and then the material will retain kung ano mang section yung um, na na form niya, no, during the rolling process. Okay? Then when we say cold form sections, so these sections are created by bending yung mga tin plates natin. So usually, ito yung nakikita natin na ginagamit sa installation of ceilings. Okay? So usually, this can be bent by the workers alone, no? So medyo um, the code does not have a standard with regards dun sa the dimensioning of cold form sections kasi depende sa applications yung purpose niya. So, but there is dimensions that we can refer to pero minsan hindi na siya ginagamit usually, no? So for roofing, so as purlin minsan ginagamit siya as our framing for our ceiling ginagamit siya. Okay? So for kaya secondary members lang siya kasi for very light applications lang siya. So hindi siya pwede for primary applications. When we say primary, so sila yung mismong nagkakarga o nagdadala ng kabuuan ng loading natin. Okay? Next, we have here the preferred steel type for each structural shape. As you can see for angles, plate, S shape, miscellaneous shape, channel, and miscellaneous channel shape, the preferred steel daw is A36 lang. So yung yung plain carbon steel lang natin. Okay? Uh, why? Because these sections are usually used as secondary members only. They are not the main resisting elements of our structure. So, kumbaga, added support lang siya. Kaya, hindi kailangan na sobrang taas nung kanyang strength and yield stress. That's why it is preferred na A36 lang siya. Okay? Then, but for HPNW, yan, we need to have grade 50 and A992 steels because this type of shapes are usually used as a beam, as a column for our structure. And since they are the main resisting elements of our structure, they should have the right and the correct tensile and yield stress to be able to support the loadings that it will be subjected to. Okay. Then for pipe, we have A53 grade B. Then for HSS, A500 grade B. Okay. So um, these shapes are important to understand so that when we try to assume or to use these sections, we have an idea what type of material we will be using or suggesting to our client so that we will not violate any of the requirements set by the code. Okay. Next, we have the different type of structural steel members existing on our structures. First, and the one that we will be discussing after this introduction is the tension members. Okay, so tension members are subjected to pure tensile forces, meaning the members are always subjected to a pull force. Okay, so the tendency of the member is to elongate. That is why these tension members are usually observed in trusses and stay cables and suspenders sa suspension bridges natin or as sagrad or as bracings in our framing. Okay? Kaya yung mga common shapes na ginagamit sa kanya are these shapes. Okay? So, we will discuss further yung treatment for tension members. But, as you can imagine here, when we have our framing here, so let's say a wind will be subjected to an earthquake dun sa frame natin, the building will tend to sway this way. Okay? When it tend to sway that way, our tension member tends to elongate. That's why it is called a tension member. That member is a tension member because it receives the movement of the material of the components to that exaggerated part. Okay, that is why that member resists any movement on that direction. Okay, then we have also compression members. So compression members generally resist axial forces or axial compression forces, sometimes called columns, posts, or stanchions. Um, and yung itsura niya or some of the most common uses niya are as follows, no? Yung circular hollow sections, we can observe this in our flagpoles, electrical posts. Okay, so that's why those type of sections are being used kasi they are better in resisting axial forces. Then we have beam sections. So beams are subjected to transverse loading, and the most efficient when their area is distributed so it's located to general practice distance from the neutral axis. So it's called it's stated here that it is subjected to transverse loading because when we have a beam, let's say for example a simply supported beam, okay? So this is our beam, and then we have a distributed load applied on it. We can see that the cross-sectional shape, so when we cut the section, you can see that the cross-section has a loading transverse its main axis. Okay, so meaning the distributed load is about this direction. Okay, so the most common beam shapes down use are wide flange, I-beams, as well as yung mga rolled I-shaped sections natin na tinatawag na miscellaneous shape, which are much more smaller than the W shape and S shape sections. Okay, so for beams known as lintels, carrying loads across a window and door openings, angles are usually used. And for beams known as skirts, in wall panels, channels are frequently used. So as you can see here, maybe you are wondering or you have been wondering, um, paano yung member dito, no, sa mga pinto natin. Di ba usually, meron pa yan. Minsan may hollow blocks, ano, may mga palitada pa yan. Minsan magtataka tayo, paano ngayon nakikerry itong portion na to kung hollow, kung butas tong area na to. Okay? So, hindi, although may tulong naman yung hamba natin, yung framing, yung door frame natin, dun sa pag-carry nung mismong loading natin. Pero it is not enough, no? That's why we introduce lintel beams to windows and doors. And for steel, yung itsura ng lintel beam is like this, no? So, it's being embedded dun sa mga patong natin. For this example, we have bricks, no? Na as our um, material. And then makikita nyo dito sa ibabaw ng door, itong steel material na to is naka-offset siya by some length para kumain siya doon, no? And then para parang nag-aakas support to, no? And then this steel beam carries whatever is the weight na nandito sa portion na to. Okay? Then for girts, usually kapag yung sa warehouses, maybe you are wondering how do they install yung mga side coverings ng warehouses natin. So, nag-install sila ng girts. Okay? So, these girts are equally spaced na sections, steel sections. Okay? Na hindi lang basta lagayan ng installation, ano? It also serve as a support or as a cover para dun sa mismong ano natin. So, whatever is yung tatama na wind dito sa portion na to, ita-transfer niya ngayon dun sa column natin dito sa portions na to, mga supports niya. Okay? So, ito yung ano. So, yung itsura niya in actual is ito. Ganito yung itsura niya. Okay? So, yan. So, yan. Next, we have beam columns. So, beam columns, when simultaneous action of tension or compression along with bending occurs or combined, long load problem arises. So meaning some columns um, has do not only experience actual load. No? So sometimes it is also subjected to moments, and when it is subjected to moments, sometimes it behaves like a beam. That's why later in our course, maybe we will be discussing this type of sections wherein our column is also behaving as a beam. So we need to check whether our our section is capable of withstanding the um, the bending force that it is subjected to it. Next, we have three general categories of steel structures. We have the frame structures, shell type structures, and suspension type structures. So for frame structures, uh, we have elements such as tension members, columns, beams, and members under combined bending and axial load. Okay, but for frame structures, this means that the main resisting elements are the beams and columns, okay? The secondary beams. So meaning 'Pag sinabing frame structure, it is a skeleton or skeletal system ng structure wherein kahit wala kang wall, wala kang slab, the frame itself is sufficient or it can resist the loadings already. Okay, so the slab and the walls are just being installed in these structures to help the loadings to be distributed dun sa mga framing niya. So, halimbawa yung left slab natin. So, ini-install siya siyempre para maapakan natin yung floor. But besides that, para ma-distribute do sa iba't ibang parts nung framing natin, yung mismong loading that is being experienced by the slab. Okay. Then we have shell type structures. So shell type structures, also commonly known as plate structures. So these are um, very less yung thickness niya compared with other structures, and yung self-weight niya are usually lesser. Um, as you can see here sa example natin, we have the King's Cross Rail Station. As you can see, the aesthetic din na gagawa nung type ng structure na 'to. So, it also serves yung purpose na mas mataas yung clearing nung floor from the roofing, which invites a natural ventilation dun sa station natin. So, mas lesser yung consumption sa electricity siguro, 'no? Dahil mas natural or um, easily flowing yung mismong um, wind natin dun ah, sa station na yan. Okay? Then last, we have yung mga suspension type structures. So suspension type structures, pinaka magandang example is a suspension bridge. So when we have our suspension bridge, ayan, as you can see here, yung main parts dito, we have cables, suspension cables na natatension kasi sinusuportahan niya tong carriageway natin. So, ibig sabihin tendency niya is bumagsak, so nag-e-elongate siya ng pagganyan, ano? And as you can see dito, yung sa cable naman along dito sa between piers nung bridge natin, naka-parabolic siya. So parang inaano niya yung dinidepict niya yung parabolic shape ng saging or yung mismong moment diagram natin. Kasi sabi, yung suspension type structures are more efficient when the shape is closely the same nung ating moment diagrams. Okay? So, yan yung example natin, George Washington Bridge. Okay? And then last, we have yung design philosophy. So when engineers start to use different materials, okay? So at first they don't know that we need some assumptions, okay, or some factor to consider when we are designing. Dati, kung ano lang yung nakasanayan nila, yun lang yung ina-adapt nila. Pero as time goes by, okay, may mga um, may mga occurrences na nangyari, may mga earthquake, may typhoons, may hurricane na nangyayari na nag-push sa kanila na mag-develop ng allowance dun sa design ng mga structures natin. And these allowances and considerations are being adapted dun sa present codes natin. That's why during the past 20 years or so, yung structural design in general has been moving towards a more rational and probability-based design procedure. Okay? So, ibig sabihin, based from dun sa mga na-experience na ng iba't ibang structure sa buong mundo, sa iba't ibang sakuna, nakapag-generate sila ng mga assumptions or allowances na pwede natin i-consider once we design new structures. And may tinatawag tayong mga limit states. So, limit states are defined as those conditions of a structure at which it ceases to fulfill its intended function. So meaning, ito yung kailangang ito yung iniiwasan natin ma-achieve ni material natin. Kasi once na na-achieve natin tong limit state na to, our material or our structure in general will not be usable. It will not perform its intended purpose, or it will not be usable by its inhabitants. So, kaya itong limit state na to, it is further categorized as strength limit state or serviceability limit state. Pag sinabing strength limit state, it is more focused doon sa safety natin. So, yung mga limit state na kasama dito or phenomena na kasama dito are yung halimbawa, pagbabakel ng mismong section natin, fatigue, no? Or yung pag-failure ng material natin over repeated loading, okay? Yung pag-fracture niya or pag-overturn or pag-slide ng member natin or ng structure natin. Then we have serviceability. This is more concerned dun sa occupancy ng building natin. So pag sinabi occupancy, example niya, bawa pag may nakita natin na deflected na yung shape ng member, when the structural member is deflected, parang by logic, we already know that we need to prevent going to that place kasi it might collapse kasi nagde-deflect nga siya. Or kapag sa vibration, when we experience a very strong vibration dun sa area, halimbawa sa floor, we know that um, the floor system is being stressed beyond its allowable stress. Kaya the stronger the vibration, the unsafe the structure becomes. And we have permanent deformation and cracking. So when we design the different components of our structure in this lecture, in this course, we will always measure or check for the limit states. Okay, and the code, the ASC construction manual, and the NSCP has different requirements uh, that we need to satisfy before we can select the most efficient section that is desired to our structure. So with this, we have three different design philosophies. We have the allowable strength design or ASD, plastic design, and load and resistance factor design. So when we say ASD or allowable strength design, this is the more traditional or classical design methodology. Or tinatawag nga siyang elastic design or WSD in concrete. Okay? So in this design philosophy, ang nangyayari, yung ating loadings are kept as is. Meaning, when we estimate the loadings on our structure or subjected to our member, wala tayong factor or multiplier na ini-introduce to account for overloading. Okay? So, we are just using what we think is the loading based from prescribed by the code, ano? Um, pero to account for the design, ang ginagawa naman, yung capacity or yung side ng allowable strength ng mismong section natin is pinapababa naman niya. So, ito yung kailangan i-satisfy, no? So, sa required strength, yung loading natin, retain siya as is. Pero yung sa capacity natin, nag-i-introduce siya ng divisor. Okay? So, on the next module, mas maintindihan natin to. Pero dito meron tayong mga tinatawag na safety factors. So safety factors are greater than 1.0. So when we tend to divide a number by a very large number or a large number greater than 1, our capacity tends to be smaller. So kung capacity natin ay smaller, so mas makakapil tayo ng section na mas angkop lang dun sa required loading natin. Okay, so that is what allowable stress design mean. So for plastic design naman, so yung consideration niya is a failure condition rather than the working load conditions. So meaning we exercise na yung material natin will will be usable until it reach yung ultimate strength stage niya, yung FU natin. Okay? So The design procedure daw is roughly as follows. I-multiply natin yung working loads by a load factor to obtain yung mga failure loads natin. Then based from these failure loads, we determine the cross-sectional shape to resist yung failure under this load. And then we will be selecting yung cross-sectional shape na yung property nito. So sa plastic design, usually ini-introduce din natin yung presence ng mga plastic hinges, which will be further discussed when we discuss plastic design in maybe at the later part ng course na to. Okay? Then last, we have the LRFD or load and resistance design. So this design philosophy is similar to plastic design in that strength or the failure condition is considered. So dito, kung sa ASD, yung loadings natin, wala tayong multiplier or magnifier sa kanya. Kay LRFD, meron tayong factor ngayon na minumultiply sa kanya na ang tawag natin ay load factors. So si load factors, tawagin natin gamma I, okay? Minumultiply natin siya sa ating mga load effects or Q. Okay, o QI. Kasi 'di ba may iba't ibang loading tayo. We have dead load, live load, environmental loads. Okay? So each load has different load factors and usually yung value ni gamma is always greater than 1. So meaning we tend to magnify the value of our loading. So let's say you have 100 kilonewton as your loading. If you are using LRFD, it will be multiplied, let's say for example 1.2. So you increase the the loading by 20% and you will design it using 120 kilonewton and not 100 kilonewton. Okay, so yun yung concept. And then dun sa capacity side, dito, sa right side, we introduce a multiplier called a reduction resistance factor. Okay, so resistance factor naman is less than 1.0. So any number multiplied by a number less than 1, it will be smaller. Okay, so like ASD, kasi baliktad naman yung kanya, dinivide naman niya, pero the value will be smaller also. So, kumbaga, the allowance na mina-minus natin dito sa capacity natin are for the unforeseen events na pwede, no? Yung mga uncertainties like for example, yung sa material, may damages, no? Hindi perfect yung pagkaka-weld niya with each other. So, yun yung allowance na pino-provide natin. That's why we are trying to introduce yung mga factors na to. Okay? So yung factored load is a failure load greater than the actual service load. So the load factors are usually greater than unity. Ayan nga. Greater than unity, and however the factored strength is reduced usable strength and less than unity. Okay? So these design philosophies are important to be understood by student. Kasi when we try to design yung mga different components natin, we need to check what philosophy is required by the problem. And sometimes both philosophy are LRFD and ASD are usually used interchangeably. Okay, so that's why we need to be more knowledgeable on these design philosophies. Okay, on the next lecture, we will discuss further the ASD and LRFD design methodology and design philosophy, and also the factors being used on these philosophies and also the load combinations to consider. Okay, but for now, this ends our lecture. So I hope you understand some of the basic um, parts of our material. And hopefully on the next topic, we were able to finish how to use the different load combinations for each design philosophy and also what factor to use or as a safety factor for ASD and a resistance factor for LRFD. Okay, so I'll see you guys again on the next lecture. Thank you.